Thanks, everyone. So yeah, my name is Sudarshan. I work at E6Data. I'll just briefly introduce the context of the talk. It's low latency programming in Java, but coding for modern CPU hardware. Even though it says Java, it's not only about Java. It's just that the code examples are Java, but hopefully some of these ideas are applicable across the board. Before I dive into the talk itself, I'll just briefly introduce E6Data. We are in the middle of fairly significant architectural changes which are happening in the world right now. Essentially, explosion in scale and the rise of object store native architectures. I think this is as significant a change as the rise of containers, right? Like the rise of containers and the cloud native stuff like created a whole new way of imagining architectures. I think this is as big a change. What does this actually mean? Essentially what it means is almost every workload class is being reimagined on composable architectures built on object storage. What that means is architectures which previously depended on other forms of underlying storage, like databases or file systems and so on and so forth, are now being reimagined, right, to work on object storage. Good example, probably the most prominent example are large-scale SQL analytics. Before, as you know, nowadays it's all about the data lake. Previously, we used to have data warehouses. Nowadays, we have data lake. What are they? Basically, what's enabling lakes, data lakes to sort of become so prominent? They are on top of object storage. We have advancements which are trying to bring all the advantages of traditional databases into this world, right? Like things like lakehouse formats, containerization, Kubernetes, distributed compute engines. Like put all of this together and you get SQL analytics on object storage. Other examples of the sort of workloads which are starting to be reimagined, we have text search, vector search, logs, metrics, traces. Like some years ago, you would not imagine any of them as being object store native, right? Like you would imagine them being in the traditional distributed database sense, like multiple nodes, each node having a local storage, that sort of thing. And if you add new nodes, you would have to redistribute the data and so on and so forth. But all of these workloads are being reimagined to work on object storage so that you don't have to worry about all of it. So what are we doing at E6Data? We are basically building a distributed compute engine for object store native architectures, primarily focused on SQL analytics now. Okay, on that note, let's get started. I'm going to show a simple benchmark, right? What is this? This is a very simple function. It's just adding two longs, right? Like two longs, and the result of it is stored in one more array, right? It's extremely simple. Now, there is some funny looking code here. Ignore that. That's just about ensuring effective benchmarking. This is a benchmark, right? I'm going to show you a different piece of code. It's exactly the same code. It's just using objects, right, instead of primitives. Not much else is different. Apart from that, it's doing exactly the same thing line by line, right? Now, what happens if I benchmark these two methods, right? This is the result of a benchmark. In Java, we use a tool called JMH. In other languages, you'll have your own tools. What you see is when you add object arrays compared to adding two primitive arrays, there's a big difference in throughput. Like the first one, you can do around 12 ops per millisecond. In the second one, we do around 181 ops per millisecond, right? That's 15x. And what is different? Nothing, right? Like literally just this one is working on primitive arrays. This is working on object arrays. That's it, right? Like why? I think the good portion of the talk is really focused on understanding why is this so much faster, and therefore what can you do in terms of how you write your programs to benefit from these sort of changes, right? And a lot of it is under, there's a phrase I think most of you will be familiar with called mechanical sympathy. Uh, Anyone not familiar with that phrase? So mechanical sympathy basically says, if you're working on something, you need to know how that works. It comes from, racing car industry. The idea is like, how do you get the maximum performance out of your car? You need to open up the hood and understand how everything is wired. Then you will eke out that last extra performance, right? This phrase has been around for over 14, 15 years now. What we are now going to talk about is some of those mechanical sympathy concepts which underpin why that performance difference exists, right? First and the most important thing to know is the differences in the latencies of our cache hierarchy, right? Like as you guys know, we have multiple layers of caches and we have main memory. And just look at what is our latency. Like if you are accessing just from registers, like our CPU cores, of course, like operate on registers, like then you effectively get a latency of 0.3 nanoseconds. That's how long it takes for data in the registers to be processed by your logic units, right? If your data is in the L1 cache, it takes 1.1 nanoseconds. And as you can see, as things go down, it's like orders of magnitude. And if you're going back to the main memory, it's around 60 plus nanoseconds, right? So the difference between L1 cache and main memory is almost 60x, right? Like if your data is in the L1 cache, the amount of time it takes to process that versus the amount of time it takes to process if your data is in main memory is around 60x, right? That's the number one thing to understand. Next, okay, yeah, how do these things actually work? Like what's actually happening is when the CPU, like if you have a simple add instruction, right? Like I want to add A and B, it's going to check first, is the data I need, A and B, in my caches? It's going to check L1, L2, and L3 cache. If it's not, it's going to go to the main memory. But what is it doing in main memory? It's not just picking up A and B and bringing it into cache. It depends on something called a cache line. Like cache line is the bus which transfers data from the main memory into your caches, right? And typically your cache line is 64 bytes. Now A and B might just be 8 bytes, but it's not bringing 8 bytes. It's bringing 64 bytes because that's the width of your cache line, right? That's the second thing to understand. Like your cache line is bringing far more data than what you actually need, but it's bringing sequential data. If this is what you want, it's going to bring this, right? Like it's just going to bring contiguous sections in the memory. The next thing to understand is something called SIMD, single instruction multiple data. This is one more modern, by the way, I say modern, but these have been around for around 15, 20 years. But these concepts are still the dominant concepts. Like it's not, these are still very relevant. Even today, when Amazon brings in newer generation of hardware, right? Like you would have heard Graviton 1, 2, 3, and 4. Well, the big difference will often be the size of your SIMD registers, the size of your cache line, the amount of memory in your L1, L2, L3 cache. Like these are still the underlying primitives, right? So what is SIMD? When you add two numbers in a scalar operation, the pre-SIMD world, you would bring in A into your register, bring in B into your register, you would add it, you would get a C, right? And then you would do the same thing again and again. Like, there will be 4 sets of operations here. In SIMD, you have registers which are long. You would bring all the data, put it into the register, all the data, put it into the register. In one operation, you would process all of them, right? Like single instruction. In one instruction, you're processing multiple pieces of data, right? And often one of the biggest advancements is increasing your SIMD register size. Then you immediately get an incremental performance boost. Another key concept is CPU pipelining and branch prediction. What does it mean? Let's take a simple instruction, right? Like let's say I'm ANDing 2 registers and storing it in a third register, right? Now, what does it mean? Like, what is the sequence? First, I have to load AND, the word AND, like the instruction. I have to decode it. I have to then load the first operand, I have to load the second operand, and I have to process, execute, and I have to store it back, right? Like if it were doing all of this in sequence, each of this is one clock cycle, a single instruction would probably take 5 to 6 clock cycles, right? Like and then every instruction is 5 to 6 clock cycles. It is all sequential. Modern CPUs don't do that. They do something called pipelining, where you start the processing of the first instruction, and before it completes, you start the processing of the second, and while it's still happening, you start the processing of the third, so on and so forth. And why does it do that? Because it's broken up your stages into, like, this is the fetch stage, this is the decode stage, this is the operand fetch stage, this is the execute stage, so on and so forth. So once you're done, and each of these are different pieces of hardware, right, in a core. So once the fetch is done, it will fetch the next instruction. Once the decode is done, it will decode the next instruction, while other steps in the core can continue. The problem with this model, though, is that what happens if there's a branch, right? Like, I've fetched an instruction, and immediately I'm going to fetch the next instruction, and so on and so forth, right? Like, I'm assuming my instructions are sequential in contiguous sections of memory. But if there's a branch, what will happen is, depending on the branch, you may have to have fetched some other instruction, right? In this case, if this branch held true, you have to go all the way here, which means all that you did here was wasted computation. You have to go back and clear out all of this and then process this, so on and so forth. So you lose the benefits of pipelining when you have branches, bottom line, right? So what I've described so far is just some of the underlying concepts of modern CPU hardware. Now I'll talk about how do you take advantage of these concepts, right? Like what is it that you need to do to take advantage of these concepts to get the sort of benchmarking differences that we saw earlier. So I'll just quickly revisit the benchmark. Like, we saw that adding two primitives is an order of magnitude faster than adding two objects. Why is that? Well, some are obvious reasons. Firstly, if you use the Linux perf tool, it will actually give you some key metrics. One of the first metric it gives is the number of instructions in an object array is almost 3x the number of instructions in a primitive array. Why is that? Well, because in the end, what the registers are operating on are the primitives, are these fundamental pieces of data, right? Like, you need more instructions to convert objects into primitives and back and forth, right? Like, that's just logical. So you can imagine if this is all it was, your benchmark should have at least a 3x performance difference, because 3x instructions means 3x slower. It's very obvious. So you should not use objects if you can avoid it, because of course you'll have more instructions to process it. Fine, that's one thing. But is that all it is? There's also L1 data cache misses. Like, why is there such a big difference? Now, this is not a huge difference you can imagine, but remember, if you missed an L1 cache, you're going back to main memory, which is 60x. So this might be a small difference, like you got just 1,000 more L1 cache misses, but that impact of the 1,000 is multiplied by 60 because you're going back to main memory, right? So why is there far more cache misses, L1 cache misses in object array? It's because of a simple property, which is primitives are allocated continuously in memory, right? Like, if I say I want an array of 100 ints, right? It is allocated, that's 4 into 100, that's like 400 bytes allocated contiguously in memory. So you remember how the cache line was pulling 64 bytes at a time? What will happen is, if you're operating on ints, that's 4 bytes. In one memory fetch instruction, you're pulling 16 integers, right? So if I were adding 16 integers, one memory access, and I'll get 15 sequential cache hits. But if I create 16 integer objects, I don't have a guarantee that they are sequential in memory, because when you're creating an object, you will tend to get wherever the allocator finds that memory. Maybe you got lucky and all of them were in the same chunk of memory and you got contiguous allocation, but you could be unlucky and you'll get some from one block and some from another block, in which case you will get a lot more cache misses. So primitives, you are guaranteed to get sequential contiguous memory, objects you're not guaranteed to. So you'll get more cache misses. There are a lot more branch prediction misses in the object array. Why is that? Well, actually, it's not obvious why you even have branches in the code we had, right? We didn't have any branches apart from the loop. Of course, there'll be a branch in the loop itself, but why did we end up having branches? It's because objects internally have to be memory safe, right? Like they will check, is there a null in here before I sort of process myself? Is my memory location safe to access? There's a lot more happening inside an object's implementation. So you get a lot of branches, even though you don't think there are branches, and that's why you get some branch prediction misses. So, okay, that's fine. You could say, maybe, because E6Data is a database engine, we have to worry about this day in and day out. Like we have to, optimize our code for sequential memory. We need to optimize our code for cache hits, that sort of thing. But you're an application developer. You could ask, sometimes I need objects. I need to model the domain that I operate in. I can't exactly just work on primitives, right? Like my domain is not just ints and longs. They are these genuine objects like transactions, like order items or shopping carts and so on and so forth. Now, you may not need low latency, so take this with a pinch of salt. But if you do need it, earlier Amod talked about Tiger Beetle. I don't know if you visited. Like one of the headline strategies Tiger Beetle uses, the way they got that 1000x, right? One of the key strategies they use is they batch things up. They don't process one transaction at a time. They do 10,000 transactions at a time, right? Now, what does that give you? When you process 10,000 transactions at a time, you can work on arrays of things, right? Not one thing. What happens when you work on arrays of things? You can model your objects differently, right? So you may have objects, but perhaps you could model your objects as working on byte arrays. Remember, byte arrays are sequential and contiguous. So you can get some of the same benefits by modeling objects on top of byte arrays. And before you say, why would I do that? Like, remember, this is if you want a low latency. Maybe you don't, then don't worry about all this. But if you do, a good example is, how do you model an array of strings? Just model it as a byte array, where the beginning of each string, you just store the offsets. So you've got two contiguous sections of memory where you're operating on here, as opposed to if you had an array of strings where each object is in a different section in the memory, potentially, right? When you need to really do low latency programming, your entire object is modeled as offsets in byte arrays. I think one of the standard techniques of low latency programming in Java world, I think if you're C++, you get it naturally, is you claim a huge byte array and manage it yourself and project objects on different sections of the byte array. And that way you get contiguous allocation, right? Now, what is the advantage of doing it? Let's look at some simple string operations, substring and trim, right? If you do it as a wrapper on a byte array, you're effectively getting 2x the performance for substring, and on trim operation, you're getting 4x. And depending on your operation, you can get much more sort of performance. But there are some things to worry about when you do this, right? Like when you do things, when you're so worried about memory and cache lines and stuff like that. A simple example of the sort of thing where you can trip up. Let's say you're doing multi-threaded programming. Here we have 2 threads, right? Thread 1 is just incrementing this long. Thread 2 is just incrementing this long. In theory, there is no overlap, right? Like there is no overlap. In theory, there should be no impact. So you can pin this thread to core 1, you can pin that thread to core 2, and they are just going, right? Like there should be no synchronization, there should be no interaction. It should have been perfectly independent sort of implementation. But in practice, that's not true. And why is it not true? It's because of cache line again. Like A and B potentially may be side by side in memory. So each core may have pulled both into their caches. So what could happen is, even though they are not sharing, effectively the CPU thinks they are sharing because the same data is present in multiple caches. A simple SIMD example, this is a piece of code to count bits, right? Count set bits in an integer. An integer has 4 bytes, that's like 4 into 8, 32 bits. How many bits are true or how many bits are false? You could ask, this is a contrived example, but there are cases, databases are a good example where you need to model some concepts as, for example, is this value null or not? You need to model it, right? And you could model it as a bit. And you could model a set of values as whether they are null or not as a set of bits. So that's a reason why you might choose to do something like this. Now the same example using SIMD, like don't worry about how the code is written. This is Java's SIMD API, vector API. It has concepts like lanes and stuff. Like it's like basically saying, I have a SIMD register. I need to load data into the register, and I have to copy data from main memory in sizes of that register. So all this API is to express such concepts, right? So ignoring the code, you can just say this is a SIMD version of the previous code. And what do you see? You see 4x performance difference simply because you're leveraging SIMD. And SIMD, we talked about it. It's a register which is, in this case, it was probably it was probably 4 times long as a basic integer. So you get 4x the performance. Simple branchless programming technique, like counting the number of nulls, right? Like I have a bunch of booleans. I'm just counting each boolean says whether something is null or not. I'm counting it, right? At the end of it, I have, the number of nulls. Or you can say the number of true values in this boolean, okay? So that's a very simple piece of code. Now here's the same piece of code rewritten to not have an if condition, right? Like basically I've just converted that boolean to a byte, right? And I'm saying value 1 implies true, value 0 implies false. Like in C++, that's implicitly the case, right? And the same piece of code, right? Like the only difference is I don't have an if condition. And if you look at the benchmarks, it's significantly different, almost 2x, right? Like where you don't have the if condition, that means you're getting a lot less branch misses and stuff like that. So I think I've sort of just given you guys a sense of what are the things to worry about in modern CPU hardware and how do you code to take advantage of it. Bottom line, aim for contiguous memory access, aim for simple code, avoid ifs if you can. What else? If you automatically aim for contiguous this thing, and use vector APIs when you can. And overarching technique is do batching if you can, because batches convert what seems like operations on single things to operations on groups of things. And moment you talk about groups of things, you can immediately start to benefit from contiguous memory. I think that brings us to the end of the talk. Yes, and if you're interested in programming like this, please take a photo of this and apply. Thank you. By the way, I'm curious, anyone else uses techniques like this in your day job? Yeah. Protobuf. It basically does. Protobuf is basically exactly that. Yes, you're right. It's a very common technique, yeah.
In the example where you showed calculating the number of set bits.
Sorry?
In the example where you showed the function to calculate number of set of bits, right? The set bits. Everything would be accessed from the register there only, right? There was only one integer. How would the second part of the programming help there?
Yeah, because we are here benefiting from SIMD. What is SIMD? It was basically doing multiple operations in one instruction. So you're right. Here, if you think of this entire thing as one logical operation, right? And you need one CPU cycle to execute, let's say, right? Now, if you have to do this on 4 integers, you need 4 CPU cycles, right? Like logically speaking. what SIMD does, it loads all 4 rints into one register and performs the operation in one logical instruction. So you are, this is the earlier diagram I showed, right? This diagram. It was an example for this one.
Right, but here in this particular case, these are linked operations, right? These are not independent operations.
That is correct. Like that is true. Those were linked operations, but you can almost think of it as you're doing the same linked operations 4 at a time.
I see.
Yeah, so here it's like 1, 1, 1, 1, 1. Actually, this is multiple, right? Like you can say this whole thing is. No, they are actually, what he's saying is right. This is dependent on this is dependent on this. His point is these are all sequential, but you could do the same sequential operations on multiple pieces of data at a time, right? That's the SIMD point. Like if you look at it, this is also doing the same operations. It's also dependent in that way, but it's doing 4 at a time or 8 at a time, depending on your SIMD register size. Those are, I didn't calculate them. Those are what the tools provide. Like, yes. So this is, I use the Linux perf tool. Like when you run it from command line, you can use a tool called perf. In fact, everyone uses perf to see how many branch misses you got, how many L1 cache misses you got, that sort of thing.
The example shown here, the string array, what if the data and the offset, the 2 arrays that we are trying to look at, what if both of them are so big that neither of them fit in the cache, L1 cache? So when you want to access a piece of data in, let's say, byte array data, you happen to load all of it into your L1 cache, but immediately try to access offsets, which would again evict.
That's not actually how it works. So you're performing, let's say, one operation. You're doing substring. It is loading 2 pieces of data, right? Like the byte array and the offsets. So in that one operation, it's loading 64 bytes. And maybe if the string is big, it may load additional 64 bytes. And it does the same for the offsets. So for that operation, it's bringing some data into cache. It doesn't need all the data to be in cache at that point in time. So the only benefit here is that in single memory access, you're getting potentially additional rows worth of data into cache. The only time you need the entire thing in cache is if you're using data structures like hash maps and stuff where you need multiple ops to happen. But in these sort of row by row operations, it doesn't need all.